Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my M.Sc. Analytical Chemistry class. Friends, I am Dr. S.R. Labhade, working as Associate Professor in Chemistry at KTHM College, Nasa. Student, in previous lecture we discussed the current sample polarography as well as current sample derivative polarography for increasing the sensitivity of analyte measurement below 10 raised to minus 6 moles. In this technique, we optimize the ratio of faradic current to non-faradic current for increasing the sensitivity of the measurement. Student, in today's lecture, we discuss another methods of current sample polarography. In order to increase the sensitivity of analyte measurement below 10 raised to minus 7 to 10 raised to minus 8 moles. Student, we know that in current sample polarography, the current measurement is carried out just before the mercury drop dislodged from the tip of the capillary. That is an electronic circuit exactly know the drop time, and therefore measurement is possible just before the mercury drop falls in the solution. In this case, the non-faradic to faradic current ratio of, in this case, the ratio of faradic to non-faradic current is optimized. Here, in this case, as a mercury drop reaches to maximum size, the surface area of the electrode becomes constant. At that time, the charging current becomes less. Therefore, by means of current measurement at the end of the life of the mercury drop, the faradic current to non-faradic current, this ratio found to be more, and therefore we can increase the sensitivity up to 10 raised to minus 6 moles. The non-faradic current have properties that the faster change in linear potential more is the non-faradic current. Generally, in linear potential calorimetry, we are linearly increasing the potential of working electrode, and if the faster change in linear potential, then non-faradic current associated with the measurement is more. Another property of non-faradic current is that after the voltage change, suddenly the non-faradic current decreases rapidly. decreases rapidly and it becomes constant or it becomes nearly to zero when potential becomes constant. Therefore, non-faradic current have two properties. First one, it changes with a faster rate with linear increasing potential. If we avoid the linear potential sweep program, then we can minimize the interference of non-faradic current. Second property, after voltage change suddenly, if we suddenly change the voltage of working electrode, then the non-faradic current decreases rapidly and it becomes nearly equal to zero when the applied potential is constant. Using this principle, we can use another technique of polarography, and that is called as pulse polarography, and it is also called as chrono-amperometry. By using this principle, the interference of non-faradic current can be minimized by using a pulse polarography. That means if we apply the potential pulse to the working electrode, and by means of this principle we can minimize the interference of the non-faradic current associated with charging of the mercury drop. Therefore, here with application of pulse to the working electrode, if we carry out the measurement of current, then that technique is called as pulse polarography. Pulse polarography or a pulse voltammetry. Polarography, that is a term when dropping mercury electrode is used as a working electrode, and if it is another working electrode, that is a mechanical knockers or static mercury drop electrode, then it is pulse voltammetry. The pulse polarography or pulse voltammetry, also called as chrono means time, chrono-amperometry, in which current measurement is carried out after the application of potential pulse to working electrode. Potential pulse to working electrode. Potential pulse means here we can suddenly increase the potential of working electrode for some instant. Generally 50 millisecond, that is a time in which we can suddenly increase the potential of working electrode, and within a 17 millivolt we can carry out the measurement at the end of the mercury drop, at the end of the life of the mercury drop, and that is a technique called as a pulse voltammetry or pulse polarography. Polarography, pulse polarography, that is the term used when dropping mercury electrode is used as a working electrode, and when mechanical knockers or static mercury drop electrode is used as a working electrode, then same method is called as pulse voltammetry. Both pulse polarography as well as pulse voltammetry are called as chrono-amperometry. That is a measurement of current as a function of time with application of potential pulse of the working electrode. Student, first of all we discuss how the potential pulse is applied to the working electrode and how the effect of non-faradic current decreases. In this case, current measurement in pulse voltammetry or polarography, the total current is sampled just prior to the pulse and again near to the end of the pulse. In this case, current measurement, that is current in microampere versus time. Now here, this is a time at which we can suddenly increase the potential, that is a application of potential pulse. At the beginning of potential pulse, the value of faradic current and non-faradic current are identical. Faradic current decreases slowly with time, but a non-faradic current decreases rapidly and it will be reaches to the equal to 0. Therefore here this is a faradic current and this is a non-faradic current. Generally at the end of the potential pulse, if this is a time interval, this is a end of the potential pulse. Therefore just before the end of the mercury drop and just within a interval of current measurement, and generally this current measurement is 70 millisecond before the drop dislodges from the tip of the catheter. Therefore, when potential pulse is applied to working electrode, faradic as well as non-faradic currents are identical. But when potential pulse continue for some time, the non-faradic current decreases rapidly, while faradic current also decreases some instant, but it becomes a constant. Therefore, at the end of the pulse, the current measurement is carried out just before the 15 millisecond, at which the electrode also reaches to maximum size or its area becomes constant, and in this case the non-faradic current also becomes equal to 0, and therefore here the sensitivity of measurement is increases up to 10 raised to minus 8 moles by this current sample measurement. Here two currents are measured. One is just prior to application of potential pulse, and second at the end of the potential pulse or at the end of the mercury drop. And this current is plotted as a function of a applied potential in order to obtain a voltammeter. On the basis of this application of potential pulse, the pulse voltammetry or pulse polarography are a three types. First one is a normal pulse voltammetry or a polarography. Second one is a differential pulse voltammetry. And number 3 is a square wave voltammetry. All these three are called as voltammetric method when a mechanical knocker is used as a working electrode, and all these are called as polarography when DME is used as a working electrode. Therefore, pulse voltammetry and pulse polarography does not differ widely. Both utilizes a working electrode as a dropping mercury electrode, but static mercury drop electrode is a little bit modified dropping mercury electrode, then that is called as pulse voltammetry. And if normal dropping mercury electrode, as we use a direct current polarography, if that electrode is used for this purpose, then it is a pulse polarography. In pulse voltammetry, it is also essential to measure the current just before the mercury drop. The electronic circuit exactly know the drop time of the working electrode before the and after the application of potential pulse. Therefore, working electrode in a pulse voltammetry, it is also necessary for electronic circuit to know the exact drop time of the working electrode or dropping mercury electrode. In case of normal dropping mercury electrode, the natural dropping of mercury varies from solution to solution, because here different solutions have a different density. Therefore, mercury drop or its size varies with solution to solution, and even varies with the application of the applied voltage. Therefore, natural dropping of mercury from dropping mercury electrode, its size is continuously changes. Also, that size depends upon the nature of solution, that is a density, as well as size is also affected even application of the potential to the working electrode. Therefore, to overcome this difficulty, a mechanical knocker is used as a working electrode. A mechanical knocker is used to detach a mechanical knocker is used to detach the drop after a highly reproducible time interval interval of 0.5 to 5 seconds. Due to this feature, this pulse voltammetry also called as a tast polarography or voltammetry. Tast voltammetry. German word that is a tasten means to touch, and therefore it is called as a tast polarography or chrono-amperometry as well as chronopotentiometry. Now here, in order to use a mechanical knocker, we can have a reproducible drop time. That means we can detach the drop from the capillary after a fixed time, and therefore it is easy to determine the current just before the drop falls in the solution. Sometimes the static mercury drop electrode, that is SEM-III, is used in pulse polarography or pulse voltammetry. A static mercury drop electrode consisting of a mercury reservoir, Hg reservoir, one end of the mercury reservoir is open and which is connected to a glass fine capillary. This glass fine capillary is connected to a solenoid, that is it provides a mechanism to give the mercury with a constant rate. This is also a solenoid, and here inside this there is a plunger. This plunger that takes a specific amount of mercury and it is dropped through this capillary. This is a support for this capillary, and this is a mercury drop which acts as a site for a redox reaction. Here this is a mercury reservoir. In this case, by means of this solenoid, specific amount of mercury is continuously given through this capillary, and here that drop is continuously given in a fixed time interval as the time of this solenoid is controlled. Therefore, in this case, this electrode is called as a static mercury drop electrode. It can be used as a dropping mercury electrode or a hanging mercury drop electrode also. Where we use a single drop for this total analysis, then it is a hanging mercury drop electrode, and if we continuously drop the mercury drop in the solution, then it is a static mercury drop electrode. In static mercury drop electrode, a solenoid Plugner used to control the flow of mercury from the capillary. It can be used as a hanging mercury drop electrode when or a dropping mercury electrode when a single activation of solenoid is done, then it is a hanging mercury drop electrode, and if the process is repeated, then it is for DME, the solenoid is activated repeatedly. Therefore, static mercury drop electrode can be used as a hanging mercury drop electrode when a single activation of solenoid is carried out. And if solenoid is activated in a multiple times in a fixed time interval, then it will be dropping mercury electrode. Student, now we discuss the working of normal pulse voltammetry. It is also called as a large amplitude pulse voltammetry. In which the working electrode is a static mercury drop electrode is kept at a base potential to which or at which the negligible electrolysis for the most of the life of mercury drop takes place. That means here analyte is not totally reduced, but at this potential, if we slowly or slightly increase the potential, then electrolysis would be start, analyte may be deposited. Therefore, working electrode is kept at a potential to which a minimum electrolysis is occur, and this potential is called as a base potential. Over this base potential, a series of square wave voltage pulses of successive increase in magnitude are superimposed upon a constant DC potential line. That means here superimposed over this base potential a series of square wave voltage pulses of successive increasing magnitude are superimposed. Now, if we see the voltage sweep program, the voltage sweep program in normal pulse voltammetry is like this. This is a potential. We know that it is denoted by letter E in millivolt versus this is a time. This is a minimum potential applied to the working electrode that we call here as a base potential. Here, over this base potential, a potential pulse is applied for some instant. In this way, the potential of that working electrode is suddenly increased for a 50 millisecond time. Again, it will be obtained to the normal potential, to base potential to 50 millisecond. Again, second potential pulse is given for 50 millisecond, and here if it is a increase in E volt, that will be a 10 millivolt, then it will be 20 millivolt, then it will be 30 millivolt like this. Therefore, here this is 2E, then this is 3E. 3E, then a 4E and so on. Now in this way here the potential is linearly increased, but it is in the form of pulse. Now this is a potential pulse applied for a 50 millivolt. That is a here we may say the time of application of potential pulse. Here, from this point to this point, this is a drop time. Drop time. That means when drop dislodges, for some instant pulse is not applied. Then after that pulse is applied for 50 millisecond, and then before 50 millisecond, again here is the same situation. Before 50 millisecond, before 17 millisecond, the current measurement is carried out. That means here potential pulse are applied with increasing potential. Here potential is linearly increases. Potential pulse are linearly increasing, and current measurement is carried out just before the drop falls in this way. Therefore, here two current measurements are carried out. One is here and another is here. That is a 15. Another is 17 millivolt before the drop falls or dislodged into the solution. After a fixed waiting period, the current measurement are carried out. First, just before the application of potential pulse, before the application of potential pulse means this is a current that is associated with some non-faradic current. This gives the baseline, and second, just before, that is 70 millisecond before 17 millisecond before the mercury drop, and the second measurement just 70 millisecond before the end of the potential pulse. This second measurement gives a maximum faradic current. Maximum faradic current. Faradic current. Where current output is plotted as a function of state potential a step sigmoidal shape voltammogram is obtained. The voltammogram is a current as a function of step potential. Step potential means which we are increasing successively during the application of potential pulse, and this is a current in microampere. In this case, initially a straight line is obtained, which is free from a noise. That we know it is a baseline of residual current. Then here current increases to maximum and reaches equal to limiting current. This is a limiting current. This is a residual current. Region of limiting current as well as region of residual current, both are here free from the noise. Therefore, we have exact baseline for calculation of a diffusion current. Therefore, ID can be easily determined, which is directly proportional to concentration, and at 1/2 ID, that is ID by 2, whatever the potential we have, that is E1/2. That means you know that half-wave potential as well as the diffusion current is measured in polarographic measurement, but in this case this limiting current is given by a quadratic equation that is like this. That is quadratic equation. Therefore, limiting current I limiting is equal to LFAC under root pi into under root d upon pi into t. In this equation, N is number of electron involved in redox reaction, F is Faraday's constant, A is electrode area in square centimeter, C is concentration in millimoles, that is an analyte concentration, D is again diffusion coefficient, measured in square centimeter per second, pi is constant, and T is a time measure from the pulse applied. And this quadratic equation is used for calculation of limiting current, or when limiting current is known, then C can be determined. That is, concentration can be determined when electrode area is known. I limiting is equal to N into F into A into C under root D upon pi into T, where N is number of electron involved in redox reaction, F is Faraday's constant, A is electrode area, C is concentration, D is diffusion coefficient of analyte, pi is constant, and T is a time measure from the pulse applied to pulse. That is a 50 millisecond in this case. That is a T here. In this way, here a normal pulse voltammetry or a large amplitude voltammetry works. Student, from our today's discussion you will find the answer of following question. Question is like this: what is pulse voltammetry and what is normal pulse voltammetry? How does it work? With this we stop here. In forthcoming lecture, we will discuss the another pulse voltammetry technique, that is a differential pulse voltammetry and square wave pulse voltammetry.